Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Okay, so now having described the very sophisticated hardness methods, how the hardness measure methods or hardness measurement is useful in finding out something else. So hardness test an approximate measure of fracture toughness of ceramics. So the fracture toughness is measured by just measuring the hardness in ceramics. Okay, so we will see in the later that ceramics exhibits very poor ductility, right? And the fracture toughness of the ceramics are very poor. But improving the fracture toughness in ceramics itself a technology. It's a huge technology and very important. We will see when we look at in the fracture mechanics aspects of materials. So here, just by measuring the Vickers hardness, which makes the pyramid impression like this, the surface will have this a square type this, and what is shown in the rose color is the cracks which just emanates from the sharp edge corners of the indenter. So assume that this is the ceramic material and this is the Vickers hardness measurement, and then cracks develops like this. So secondary cracks developed during the hardness testing can be used to assess the fracture toughness of brittle materials. Okay. So illustrated here is a schematic of such secondary cracks emanating from the diamond pyramid indenter used in a Vickers hardness test. So this is what it is. So this distance is 2a, and the end-to-end two crack ends are measured as 2d prime. The indentation length is 2a, basically a diagonal length here. Secondary crack emanate from the indentation corners and have the length of 2d prime and measured on the sample surface. Correlation of the lengths of indentation cracks with measured values of K1C indicate that ceramic fracture toughness values correlate with this lengths as K1C. K1C is equal to alpha naught into E by H to the power half into P by D to the power 3 by 2, where E is the material modulus, H its hardness, P the indentation load, and 2d prime the secondary crack length. The value of toughness is expressed in mega Newton per meter to the power 3 by 2 if the constant alpha naught is taken as 0.016, and the other terms in the equations are in SI units. The value of alpha naught is accurate to about 25% as determined by the correlation of indentation fracture toughnesses with those obtained through more fundamental means. You see, it is quite interesting, right? So I said that knowing the fracture toughness of ceramics is very important, and it's very technologically also very important. So measuring these fracture toughness just by means of hardness test is also very handy. Okay, though it gives some some not very accurate but approximate value it gives, nevertheless it gives an idea about the fracture toughness. Okay. So this is another interesting aspect of measuring hardness in ceramics. Now we just move on to the next important mechanical testing called tensile test. Before even getting into the results and the description of what kind of data you will get, we will also look at the mechanics aspect of tensile test. Since we have spent a lot of time in mechanics aspect, so it's better to correlate then and there. That helps. So what is involved in a tensile test? A tensile test normally conducted on a cylindrical bar or a plate with a specific geometry. We are not talking about that. We are simply taking a rectangular bar or a sheet in a 2D and then subject them to tensile force like this, and the area of the cross section is A1, and the force, the tensile force is F1 here. So the sigma 1 is F by A1. So that is what it is. So resolution of a tensile stress into a shear and a tensile stress on a plane rotated by an angle theta to the tensile axis. Okay. The shear force on this plane is equal to F sin theta, and the tensile force is equal to F cos theta. So how do we understand this? So this is the shear plane, which is 45 degree. This also you understand now. That is the plane where the maximum shear stress act. So all the crystals deform by slip, and it is in this plane. Those details and all you know now. So this is axis, force axis. So this is theta, 90 degree theta. So cos 90 minus theta is sin theta. So that is how it becomes F1 sin theta. So this is F1. So this is F1 times sin theta. It becomes this shear force. That is what it is. So that sin theta comes from cos 90 minus theta. So sin. So F1 sin theta is the shear force, and then this one is a tensile force. So you just look at this direction and then take the force which is acting on this plane is not just F1, but it is F1 times cos theta is the magnitude of the tensile force acting on this. So that is what it is here. So we have already, since we have already spent a lot of time on how to resolve this test and all that. So this is the one good example application of your knowledge in a simple tensile testing. The area of the rotated plane is equal to A1 by cos theta, where A1 is the transverse cross-sectional area normal to the applied force, such that the normal tensile stress sigma 1 is equal to F by A1. Okay. Thus, the resolved shear stress on the rotated plane is tau is equal to F by A1 times sin theta cos theta. The corresponding tensile stress is sigma is equal to sigma 1 cos squared theta. So how do we get this? So the shear stress is shear force by the shear stress acting on the area. So which is equal to F by A1 sin theta cos theta. Okay. So you need to understand that the rotated plane is much larger than this. So that means larger by what amount? Larger by 1 by cos theta. It is larger than by 1 by cos theta. So that is why it is written like that. So this can be written like this: F by A1 is equal to sigma 1. That's the only principal stress in the tensile stress or tensile test. Sorry, sigma 1. Okay, so which can be rewritten like this: 1 by 2 sigma 1 sin theta. Why do we write in this form? Because we can represent this, the whole state of stress, in a Mohr circle, which is always plotted with a 2 theta. This procedure also we have seen. So now we can see the application of that later. So this is a shear stress, and then tensile stress is F by A1 cos squared theta is equal to sigma 1 cos squared theta, which can be rewritten like this: 1 by 2 times sigma 1 into 1 plus cos 2 theta. Okay, so this is in trigonometric identities. So we can now plot this in a Mohr circle to understand that concept again. This will again give an opportunity to recall what we have already learned. So what is shown here? It is, as I told you, this is the only principal stress in a tensile test is sigma 1. So which will form a, so around this we'll make a circle. So that becomes a diameter. Sigma 1 is become a diameter of a Mohr circle. And then, so this is what is written here: a Mohr circle representation of the stress state corresponding to the situation in the figure 1. Uniaxial tension is represented by the circle with the diameter equal to sigma 1. This is what I just said. The intercepts of the circle on the tensile stress axis are 0 and 1, sigma 1. So this is 0 and sigma 1. This is the two intercepts of the circle. A plane rotated by the angle theta with respect to the plane of the principal stress has a shear stress acting on it as shown. So here this is theta. So in Mohr circle we plot it as a 2 theta. So 2 theta, wherever it intersects, it gives a corresponding tensile stress and a shear stress. So whatever we are now showing as a resolved shear stress and tensile stress also can be obtained by simply plotting on the Mohr circle here. So this is corresponding shear stress and this is corresponding tensile stress. So the maximum shear stress has a magnitude of sigma 1 by 2 and it is found on the plane rotated 45 degree from the tensile axis. So this also we know. So that will come here. So the 2 theta will become about 90. So theta will become 45. So that is also we know. So the next one is what will happen if you subject the specimen by biaxial tension. Okay. Another simple interesting problem. Suppose a second principal component of the stress can be considered. Here the nominal second stress is sigma 2 is equal to F by A2. So here we are talking about this is sigma 1 and this is sigma 2 in this direction. So same figure, but then you see that the stress resolution takes place here, which is shown here. You can see that this is F2 because this direction, and then this is the normal force and the shear force and the normal force is given like this. So here the shear force is F2 cos theta and the normal force is F2 sin theta, which is already we have seen. But this stress reduces the shear stress on the rotated plane and also alters the tensile stress there. So very important point. We are talking about a biaxial tension. So the secondary principal component of the stress is going to reduce the shear stress, what is being already there in the uniaxial tensile test. So here the maximum shear, the shear stress is given by the difference in the two principal stresses times the sine 2 theta. Okay, so we can just again we can write the tensile stress, which is equal to half time sigma 1 into 1 plus cos 2 theta plus of sigma 1 minus cos 2 theta. So we can write it like this. So this is a combination of two principal stresses plus the difference in the principal stresses times the cos 2 theta. That is your tensile stress. So we can plot them again on the Mohr circle. Here what we are seeing, here we are talking about two principal stresses, sigma 1 and sigma 2. The difference between the sigma 1 and sigma 2 forms the diameter of the Mohr circle. Okay, so that is sigma 1 minus sigma 2 is this. So this is what is written. Circle has a diameter equal to the difference between the magnitude of the principal stresses. The intercepts of the circle along the tensile stress axis are sigma 2 and sigma 1. And here a plane rotated by an angle theta with respect to the original axis has the shear stress component illustrated. So rest are the same. We know that this is 2 theta. So this is sigma and this is shear. The maximum shear stress is again found on a plane rotated by 45 degree. However, in this case, the maximum shear is sigma 1 minus sigma 2 by 2. This is important. There it was sigma 1 by 2 maximum, but here it is not sigma 1 by 2, it is rather sigma 1 minus sigma 2 by 2. So this is another way of looking at this. Now we'll go to engineering stress strain curve. Okay. So normally in any textbook, the engineering stress strain is illustrated like this. So what is plotted here is the average stress versus conventional strain. So you can see that the average stress goes like this and reaches a maximum and it comes down. The stress used in this stress strain curve is the average longitudinal stress in a tensile specimen. This is obtained by the load by the original area of cross section of the specimen. So that's important. Whenever we talk about engineering stress, we divide the load by the original area of cross section. Okay. So what are the descriptors here? So we are showing something. Since this curve is continuous, so to find out the yield strength, there is something called offset yield strength is defined. We will see it how exactly we can do that. And there is something called uniform strain, which goes up to the maximum, and the strain to fracture up to the fracture point. And then you have offset yield strength, tensile strength, and the fracture stress. So many parameters are already denoted on this stress strain plot. So we will thoroughly look at all of them one by one, very slowly. Okay. So the engineering stress is represented by S in this textbook. So I have just followed this reference mostly for this section, which is in data. The engineering stress is given by S, which is equal to load divided by the original area. The strain used for the engineering stress strain curve is the average linear strain. So if you recall, when we introduced the stress strain in the elasticity, there also I use the same terminology, average strain, right? Average strain and average stress. So you have to now see that we are now talking about a bulk property. So you have to connect what is a strict definition of a strain and a stress. But we are talking about average stress and average strain, which is obtained by dividing the elongation of gauge length of the specimen, which is delta, by its original length. So E is equal to delta by L naught, which is equal to delta L by L, which is equal to L minus L naught by L naught. Since both the stress and the strain are obtained by dividing the load and elongation by constant factors, the load elongation curve will have the same shape as the engineering stress strain curve. So this is so what is shown here is another interesting idea you have to keep in mind. There is something called the recoverable elastic strain. We have to understand what is this recoverable elastic strain. So look at this diagram little carefully. Now this is a load versus elongation plot. First, the specimen is loaded from 0 A and then it is unloaded. It just crosses the yield point and then got unloaded to the point A dash. Then what happens? So corresponding to this point A, the strain is somewhere supposed to be here. But what is that we are landing? We are landing at A1. So this OA dash is the permanent strain, but A dash to this point, that is B, it measures as a B, is a recoverable elastic strain on unloading, which is B is measured as sigma 1 by E, which is nothing but P1 by A naught divided by E. So this is recoverable. Okay. The permanent plastic deformation is offset A. This is offset A, which is shown in the figure. So the A is permanent deformation, plastic deformation. B is the recoverable elastic strain. So what is important here? Point is, note that elastic deformation is always present in the tension specimen when it is under load. Okay. If the specimen were loaded and unloaded along the path O, A, B, B dash. So O, A, B, B dash. So we are going further away, okay, with the higher loads. Okay. The elastic strain would be greater than on loading to P1 since P2 is greater than P1, but the elastic deformation D would be less than the plastic deformation C. Very, very important. So now we are now crossing this point A, continuously going all the way up to B and unloading and reaches point B dash. Then you just compare what is the elastic strain would be greater than on loading to P1. So elastic strain will be greater, okay, but the elastic deformation D is much less than the plastic deformation C. So you see earlier the difference is not much AB, but as you go higher loads, the D becomes the elastic recoverable strain. Elastic strain is much smaller as compared to the plastic deformation. So this point we have to keep in mind. We will see how all this small subtle differences will help us in understanding material behavior, especially when we go to different type of loading, combinations of loading, right? Cyclic loading. All these small factors will contribute in understanding. Okay.